Welcome to today's on-demand webinar about the use of Polyclar 10 stabilizers in beer. In this presentation, we will talk about what beer stability is, how haze is formed, and how haze is prevented. We will then talk about Polyclar 10 stabilizer for beer, its method of application, and advantages. What do we mean by drivers for beer stabilization? We want to answer the question of why should a brewery spend money to stabilize their beer. Consumers expect better quality and product consistency. The new breweries are larger with expanded distribution areas. Beer has to travel further from the brewery, and this requires a longer time for the beer to be kept. There is a challenge in producing quality products in developing markets that can compete with imported beers. Domestic producers don't want imports to take over. There is also a need to reduce costs, both production costs and in return beer costs. Beer is sometimes returned to the brewery if something is perceived to be wrong with it. There is also potential loss of market share from someone not having a good experience with their product. A suitable definition of beer stability is the ability of beer to resist the formation of non-biological colloidal haze. The end of useful shelf life in beer is generally considered to occur when a beer develops haze of at least 2 EBC. At 2 EBC units, you are visually able to perceive haze. To demonstrate the impact of environmental stress on beer, we took packaged beer and subjected it to different environmental conditions. One lot was stored cold, one lot was stored at 40 degrees Celsius, one lot was cycled between 40 and 0 degrees Celsius 24 hours at a time, and one lot was kept at 40 degrees Celsius and also shaken at the same time. Shaking beer at high temperature produced more haze than any other storage condition. This has a lot of practical implications, particularly in countries where the summer temperatures are very warm and the beer has to travel in trucks on very bad roads. These beers will be prone to produce much more haze. The haze precursors for formation of haze is complexation between haze-giving polyphenols and haze-sensitive proteins. The structure of haze-sensitive protein is shown here. These proteins have high molecular weights. They are proline-rich and originate from the Hordine fraction of malt. They transfer to the wort and finally to the beer, where they complex with the polyphenols and form haze. On the left side of this slide are the monomeric polyphenol haze precursors, such as catechin and gallocatechin. These monomeric polyphenols condense to form dimers and trimers. An example of a dimer in this slide is pro-delphinidin. On further oxidation, these dimers and trimers polymerize and form very large molecules called tannoids. The larger the polyphenols are in terms of molecular weight, the more polyphenolic OH groups they will have, and these OH groups then readily combine with haze-giving proteins to make protein polyphenol complexes, which result in the formation of haze in beer. Many years ago, Chopin proposed that haze in beer is formed by protein polyphenol interaction. Carl Siebert further developed this model and noted that not all polyphenols are the same. There are haze-forming polyphenols as well as polyphenols that do not contribute to haze. Similarly, on the protein side, Siebert distinguished between haze-giving proline-rich proteins and low molecular weight foam-producing proteins. It is the proline-rich proteins that combine with the polyphenols to form haze. These polyphenols have to have at least 2 ends to combine with protein in order to form haze. Polyphenols could have 3, 4, or 5 ends. If they don't have at least 2 ends, the chains could not grow. We see this practically in haze formation, where the chill haze increases with time. The longer you keep the beer warm, or agitate, or give any impetus to haze formation, the chill haze and total haze will increase. That's basically because these chains of proteins and polyphenols grow over time. This slide shows the O'Rourke model for haze formation. Even in very clear beer, when it's first filtered, the monomeric polyphenols combine with protein but do not contribute to haze formation. Even if the beer is absolutely clear, there is already complexation happening. The reason you are not seeing haze in that the polyphenols are monomeric with small molecular weights. On oxidation, the monomeric polyphenols convert to dimers and trimers, and these combine with proteins to give you the reversible chill haze. This is the haze that appears in a bottle of beer when it's chilled and disappears when the bottle is warm, say by putting a beer on your kitchen table. On further oxidation, these dimers and trimers convert to very reactive oxidized tannoids. As we saw in the previous slide, these tannoids have a number of anchoring polyphenolic OH points that make them very reactive, so they combine with protein to give you permanent haze. One thing to notice here is that the formation of permanent haze, the tannoids cross-link a number of proteins, so you get these very large tannoid protein formations. We always say that tannoids are the number one enemy of beer. For beer to be stabilized, you have to remove all the tannoids. By the same token, you have to remove about 40% of the monomeric polyphenols, which in time will give you the secondary tannoids. This slide presents some evidence for the models I've just described. For this, we did a very simple experiment. We took some beer and overstabilized it with PVPP. We used a dose rate of 100 grams per hectoliter, and at this high dose level, most of the polyphenols were absorbed out of the beer, and only the haze-giving proteins were left. Then we added 3 different types of polyphenols to the beer separately: catechin, tannic acid, and oxidized catechin. Catechin is a monomeric polyphenol, tannic acid is a tannoid, and oxidized catechin represents dimeric and trimeric polyphenols. You can see on the x-axis that these were added at different dose rates. This addition produced a dose-related response for both tannic acid and oxidized catechin. We found that catechin did not give an appreciable rise in haze formation, indicating that the polyphenols have to be oxidized before they will participate in haze formation. Here you can clearly see that the red and green lines have fairly low values at 10 grams per hectoliter compared with 50 grams per hectoliter. The dose-related response is clear for both tannic acid and oxidized catechin. This is a model of haze formation showing total haze on the y-axis and storage time in weeks at an elevated temperature of 37 degrees Celsius on the x-axis. Before we did this work, we expected this graph to show only the incline phase, indicating that haze formation is directly related to storage time. However, what we found was that this graph was biphasic. There was a clear lag phase followed by a clear incline phase. During the lag phase, a large pool of tannoids is being generated. When you get to a large enough amount of very reactive tannoids in your beer, they readily combine with the haze-giving proteins to give you the incline phase. The slope of the incline phase gives you the rate of haze formation. This is the basic structure of the building block of PVPP. The important thing to note is the relationship of the carbonyl group to the nitrogen. Because of their proximity, the carbonyl group has a very strong partial negative charge. This partial negative charge on the carbonyl group readily combines with the beer polyphenols, which have a partial positive charge on the phenolic OH group. The hydrogen bond between the carbonyl group and the polyphenolic OH group is very strong. You can see similarity between this structure and that of the amino acid proline. The preferential mechanism is hydrogen bonding, but there is also some evidence of pi bonding and polar interactions which further strengthen the interaction. PVPP selectively absorbs polyphenols and acidic moieties from the beverage. It has a strong affinity for polyphenol absorption. Interactions are based on strong bonding between the residues and the pyrrolidone rings of PVPP through hydrogen bonding, pi bond overlap, and polar and hydrophobic interactions. The predominant mechanism is hydrogen bonding. Unlike proteins and other polyamides like nylon, PVPP lacks amide hydrogen groups. This prevents chain-to-chain hydrogen bonding, resulting in stronger PVPP polyphenol interactions. This makes PVPP very efficient compared to a polyamide like nylon due to this lack of chain-to-chain hydrogen bonding. Now we'll take a look at Polyclar 10 stabilizer product and application information. Different Polyclar stabilizer grades are optimized for different applications. Our flagship product is Polyclar 10 stabilizer, which is our single-use PVPP. It is added prior to primary filtration by a peristaltic or injection pump over 90% of the beer run, and then all of the PVPP, which has bonded with polyphenols, is removed by the diatomaceous earth filter. Ashland also has a second technology for PVPP, which is our regeneration grade Polyclar Super R stabilizer. This grade can be used over and over again. Once you buy your first fill, the subsequent use is achieved by the regeneration process. You have a dedicated primary filtration and then a dedicated Polyclar Super R filter. The primary filter makes the beer clear, and the stabilization takes place in the dedicated Polyclar Super R filter, which is either a horizontal leaf or a candle filter. Polyclar 10 stabilizer is slurried in water, preferably deaerated water, to make a 10% weight over weight slurry, and is hydrated for approximately 60 minutes with the help of a high-speed stirrer. It is then dosed into the beer stream over 90% of the filter run. Stabilizing only half of the beer is not the right way to do it. You have to stabilize at least 90% of your beer to maximize efficiency. For maximum efficiency, Polyclar needs to be fully mixed with the beer for a contact time of 5 to 10 minutes. Polyclar 10 stabilizer can be added from the diatomaceous earth dosing pot together with the diatomaceous earth or from a separate PVPP vessel. It can be used at the same time as silica, but not tannic acid. Tannic acid is a tannoid, and thus it would react with the PVPP. If tannic acid is used, it must be applied sequentially with PVPP. Polyclar 10 stabilizer is very effective over a range of temperatures, but preferably the beer should be at 0 Celsius or below. This diagram shows the options for addition of Polyclar 10 stabilizer. It can be added mixed together with diatomaceous earth, but the preference is to have a separate PVPP dosing tank followed by a buffer tank to give an optimal contact time. One thing to note here is that when you use a buffer tank, you have to make sure the inlet is at the bottom of the tank and the outlet is at the top. So as the beer moves from the bottom of the tank to the top, it has sufficient contact time. Then the PVPP is captured on the filter. This slide gives some typical addition rates for Polyclar 10 stabilizer under different conditions. If used alone, 10 to 20 grams per hectoliter will give 6 months of shelf life. A much higher dose is required if more than 6 months of shelf life is required. If Polyclar 10 stabilizer is used with silica gel, 5 to 15 grams per hectoliter will give 6 months of shelf life. 15 to 25 grams per hectoliter will produce more than 6 months of shelf life. This graph shows total polyphenol reduction with Polyclar 10 stabilizer and Polyclar Super R stabilizer. Polyphenol reduction is dose-related for both grades. The more you add, the more efficient the polyphenol removal will be. Similarly, there is a dose-related response to tannoid reduction. This beer was kept at 37 degrees Celsius for the weeks indicated at the bottom of the graph. You can see the difference in tannoid removal with increasing dose rate. This graph documents haze development in beer stabilized with different doses of Polyclar 10 stabilizer and stored at 37 degrees Celsius. Again, you can see the dose-related response. Useful shelf life is indicated by the line for 2 EBC units, and increasing dose rates increase the shelf life. Predicted shelf life is indicated on the y-axis of this graph plotted against dose rate of Polyclar 10 stabilizer. Again, we see a very systematic dose-related response. The more Polyclar 10 stabilizer that is added, the longer the predicted shelf life will be. The advantages of Polyclar 10 stabilizer are that haze-sensitive tannoid levels can be controlled. Tannoids are the #1 enemy of beer, and they are to be completely removed to achieve stabilization of the beer. The formation of chill haze and permanent haze can be reduced. Polyclar 10 stabilizer is very effective at low addition rates, is applicable to all beer types, and uses existing equipment. You can use the same pot for the DE slurry for dosing, but the preference is to have separate pots. Polyclar 10 stabilizer is easy to handle and has no negative effects on the beer quality. It is completely removed from the beer with no residue. This is very important. Polyclar 10 stabilizer is a processing aid that does not need to be declared on the label. It leaves absolutely no residue in the beer while absorbing out the polyphenols. Polyclar 10 stabilizer keeps beer looking and tasting fresher longer. Thank you.